Right now above you, the night sky is dark. That sentence sounds so ordinary that your brain almost skips past it entirely. Of course, the night sky is dark. It is night. Darkness is what night does. You have known this since you were old enough to look upward and feel something quiet settle inside your chest at the sight of stars scattered across black space. Darkness and night are so thoroughly paired in human experience that questioning the relationship between them feels almost childish, like asking why silence is quiet or why stillness does not move. But here is what almost nobody realizes. The darkness of the night sky is one of the most profound physical facts in the universe. It is not decoration. It is not simply the absence of sunlight after Earth rotates away from its star. The darkness above you right now is direct, observable physical evidence that the universe had a beginning, that time itself started, that existence, all of it emerged from something rather than always having been. The night sky being dark is proof of the Big Bang, not metaphorically, not philosophically, physically, geometrically, mathematically provable from the simple fact that you can look upward on a clear night and see black space between the stars. Most people will live their entire lives without ever knowing this. They will look at the same darkness that contains one of the deepest secrets in cosmology, feel a quiet sense of wonder, or perhaps nothing in particular, and then go back inside to look for something to eat. The universe holds its greatest revelations with extraordinary patience, waiting for someone to ask the right question. The question, it turns out, is the simplest one imaginable. Why is the night sky dark? Not why is it dark right now at this hour above your particular city or forest or ocean or desert? Not why does darkness fall when Earth turns away from the sun? Those answers are straightforward, familiar, the kind of thing explained in school before anyone moves on to something apparently more complicated. The question that matters is deeper. Why, across the entire night sky in every direction you can point, does darkness exist at all between the stars? Why is the space between stars not filled with light? Why, if you look outward from Earth in any direction, does your line of sight eventually terminate in blackness rather than the blinding surface of a star? Because if the universe were infinite in space and infinite in time, if stars and galaxies extended forever in every direction and had been burning forever across all of history, the answer should be completely different. The night sky should not be dark. It should be blazing. Every single point in the sky, every fraction of every degree of arc should glow as brightly as the surface of a star. There should be no darkness anywhere. Looking upward at night should feel like staring directly into a furnace, so intense it would char the atmosphere, boil the oceans, and render the surface of Earth uninhabitable within moments. Instead, you are lying here in the dark, perfectly comfortable, perhaps slightly sleepy, listening to a quiet voice describe the universe. The fact that you can do that at all is the mystery. This puzzle has a name. Astronomers call it Olbers Paradox, named after a German physician and amateur astronomer named Heinrich Wilhelm Olbers, who wrote about it formally in 1823. Though, as you will discover, the question is far older than Olbers, and the answer, when it finally came, arrived not from an observatory or a physics department or a government research institute. It arrived first, and most clearly, from a poet writing about the nature of God and the architecture of the cosmos in the final year of his life. That detail alone should give you some sense of how strange and wonderful the path toward this particular truth turned out to be. But before we reach any of that, we need to sit with the paradox itself. We need to feel its full weight, because the human mind tends to accept the night sky as simply given as background as the way things are. The paradox only becomes genuinely astonishing when you force yourself to confront what the darkness actually implies and what it would mean if the darkness were not there. If you enjoy journeys that reach into the deepest structure of reality and come back with something that permanently changes how you see an ordinary night, to do me a small favor and hit that like button and subscribe. It genuinely helps this channel reach more people who might want to sit quietly with the universe for a while. Get yourself comfortable. Let your eyes close if they want to. The darkness is the story. Let's begin. To understand why the night sky being dark is so extraordinary, you need to imagine what a truly infinite universe would look like from inside. Suppose the universe extended forever in every direction. No edge, no boundary, no wall, at the end of space beyond which nothing exists. Stars scattered throughout all of that infinite volume, not perfectly uniformly, perhaps, but on average roughly evenly distributed, the way grains of sand might be distributed throughout an endless ocean if you stirred everything together, patiently enough. And suppose this universe had always existed. No beginning, no moment of creation, no cosmic clock that started ticking at some identifiable point in the past. Stars have been burning forever. Galaxies have existed forever. The whole vast eternal machinery of the cosmos has been running without interruption across all of time. Now stand on Earth and look upward. In any direction you choose, your line of sight travels outward through space. In the near distance, it might pass through empty space between nearby stars. Farther out, it passes through interstellar regions of our galaxy, past star clusters and nebulae, and the vast dark lanes between spiral arms. Farther still, it exits the Milky Way entirely and enters intergalactic space, crossing hundreds of thousands of light years of near emptiness before encountering the next galaxy, and then the next, and then the next. On and on in this hypothetical infinite universe forever. Here is the mathematical certainty buried inside that picture. In an infinite universe filled with stars, every single line of sight, no matter what direction you choose, must eventually intersect the surface of a star. Everyone. Because no matter how thinly stars are spread across space, if space is truly infinite, there will always be enough stars to fill every possible line of sight eventually. The probability of any given direction remaining empty forever approaches zero as distance extends toward infinity. Try to feel what that means physically. Look at a forest and imagine the trees extending forever in every direction, not just farther than you can see, but genuinely infinitely far beyond any horizon, beyond any distance your mind can reach. Stand in that forest and look straight ahead. Your line of sight eventually hits a tree trunk. Look left, another tree. Look right, another tree. Look in any direction you can imagine. There is always a tree somewhere along that line because the trees never end. Stars in an infinite eternal universe work the same way. And stars are not just obstacles blocking the view. Stars are sources of light. Blindingly, intensely, ferociously hot sources of light. Which means, in a truly infinite eternal universe, every point in the sky should glow with the brightness of a stellar surface. Not the faint pinpoint of a distant star, the full, overwhelming surface brightness of a star seen up close, because in an infinite universe, the sheer number of distant stars exactly compensates for their distance. The sky should be a continuous sheet of fire. The night sky should be, by all mathematical logic, applied to an infinite eternal universe, approximately 1,800,000 times brighter than the midday sun. Instead, it is dark enough that you can sleep beneath it. Something is wrong with the infinite eternal universe. Something is profoundly, fundamentally, universe-reshapingly wrong. And the darkness above you right now is the evidence. Now, your instinct at this point might be to reach for an explanation. Several suggest themselves naturally. Perhaps the light from distant stars is too faint to matter by the time it reaches her. Perhaps dust or gas absorbs the light before it arrives. Perhaps the universe, while very large, is not truly infinite. Perhaps the fact that the universe is expanding somehow solves the problem. These are sensible thoughts. They are the thoughts that occurred to many intelligent people across centuries of grappling with this question. And as you will discover, in time, each of them is either incomplete, incorrect, or contains the right idea in the wrong form. The real answer is more devastating and more beautiful than any of them. But right now, allow the paradox to simply exist. Allow yourself to look upward, even with your eyes closed, at the darkness above this world, and notice that you are seeing something that should not be there. You are seeing evidence of something, an absence of light that should be presence, a quiet that should be raw. The night sky is dark. That fact alone contains the entire story of where everything came from. What comes next will take us back through centuries of brilliant minds, circling an answer they could not quite reach forward through the structure of space and time itself, and finally outward toward the edge of everything humanity can. Observe where ancient light still travels through darkness that should, by all logic, not exist. The universe has been keeping this secret in plain sight since the first human being looked upward at a clear night sky and felt something they could not name. Now we go to find it. For most of human history, the night sky was simply there. People looked upward and saw stars. They named them, navigated by them, wove stories around them, built temples aligned to their rising and setting. They used the sky as a calendar, a compass, a stage for mythology, and occasionally as evidence for whatever theological argument seemed most pressing at the time. But for all the centuries of careful observation, for all the meticulous records kept by Babylonian astronomers and Greek philosophers and Islamic scholars and Renaissance mathematicians, nobody asked the question that should have been obvious from the very first night a human being looked upward and thought seriously about what they were seeing. Nobody asked why there was darkness between the stars. The question required a particular kind of mind, not a mind that accepted the sky as given background, but a mind willing to treat the most familiar thing in human experience as a problem requiring explanation. That kind of mind is rarer than it sounds. Familiarity is the enemy of curiosity, far more often than ignorance is. We do not question the things we have always known, we question the things that surprise us. And darkness at night had never surprised anyone. Then sometime around 1610, Johannes Kepler surprised himself. Kepler is remembered today primarily for 3 laws of planetary motion that bear his name, elegant mathematical relationships describing how planets move around the sun. He was a meticulous, deeply religious man who believed the geometry of the cosmos reflected the mind of God, and who spent enormous portions of his life doing calculations of extraordinary tedium in service of that belief. He was also, by the standards of his era, a genuinely radical thinker. When Giordano Bruno had argued decades earlier that the universe was infinite in extent and filled with countless stars, the Catholic Church had burned Bruno at the stake. The idea of an infinite universe was not merely scientifically controversial in the early 17th century. It carried mortal risk. Kepler disagreed with Bruno on the infinite universe, and he disagreed not on theological grounds primarily, though those existed, but on observational ones. His argument was simple. If the universe were truly infinite and filled with stars in all directions, the night sky should be blindingly bright. Every line of sight should eventually terminate on a stellar surface. The sky should glow uniformly, overwhelmingly, unbearably. It did not. Therefore, Kepler concluded, the universe must be finite. There must be an edge. Beyond that edge, darkness. This was the first time anyone had connected the darkness of the night sky to the structure of the universe itself. Kepler had glimpsed something profound. His logic was correct, his observation was correct, but his conclusion, a finite universe surrounded by empty darkness, would turn out to be wrong in ways he could not have imagined. Still, the question had been formally asked for the first time. Why is the sky dark at night? Kepler died in 1630 without a satisfying answer. The question drifted. Edmund Halley, better remembered today for identifying the comet that bears his name, took up the problem briefly in 1720. He was a practical man, more comfortable with observation than with the kind of philosophical speculation the question demanded. Halley suggested that distant stars simply contribute too little light to matter. The farther away a star, the fainter it appears. Surely the combined faint glow of unimaginably distant stars adds up to something negligible. Surely darkness wins by sheer attenuation. It was a reasonable thought. It was also wrong, though. Halley lacked the mathematical tools to demonstrate why definitively. The problem is this. Yes, an individual star at twice the distance appears 4 times fainter, following the inverse square law that governs how light spreads through space. But in an infinite universe, as you look farther outward, you are also looking through a shell of space containing far more stars. Twice as far means 4 times fainter per star, but a shell of space twice as distant contains roughly 4 times as many stars. The two effects cancel each other exactly. Every shell of space, near or far, contributes the same amount of total light to the sky, and there are infinitely many shells. The sum is infinite brightness. Distance does not save you. Halley had guessed at the answer without doing the arithmetic. The arithmetic was merciless. A Swiss astronomer named Jean-Philippe Loise de Chéseaux worked through the mathematics more carefully in 1744 and arrived at the full horror of the conclusion. In a truly infinite universe filled uniformly with stars, the sky should blaze with the brightness of the solar surface at every point. He proposed a solution involving a mysterious light-absorbing medium-filling interstellar space, some form of cosmic fog that absorbed the light of distant stars before it could accumulate into intolerable brightness. It was an ingenious idea. It was also wrong in an interesting way. Any medium capable of absorbing that much starlight over cosmic timescales would itself heat up until it glowed just as brightly as the stars it was absorbing. You cannot hide infinite light inside a finite absorber. The heat must go somewhere, and it goes into radiation. The darkness remains unexplained. De Chéseaux published his analysis, noted his failed solution honestly, and the scientific community largely ignored the whole thing. The question drifted again. Then came Olbers. Heinrich Wilhelm Olbers was a physician in Bremen, Germany, who practiced medicine during the day and astronomy at night with an enthusiasm that most professionals reserve for their primary career. He discovered several comets contributed to the early study of asteroids, and maintained an observatory in his home that became one of the intellectual gathering places of the era. He was well connected in the astronomical community of the early 19th century, corresponding regularly with the greatest mathematical mind of the age, Carl Friedrich Gauss, who remained a close friend for decades. In 1823, Olbers published a paper revisiting the problem of the dark night sky. He arrived at essentially the same mathematical conclusion as de Chéseaux, proposed essentially the same flawed absorbing medium solution, and was similarly unable to resolve the paradox. His contribution was not the solution, it was the framing. Olbers wrote about the problem with such clarity and placed it so squarely in the center of contemporary astronomical debate that it remained there, attached permanently to his name ever after. This is somewhat unfair to Kepler and de Chéseaux, both of whom had articulated the same paradox earlier, with equal rigor. History has a habit of attaching names to problems according to who framed them most memorably, rather than who discovered them first. Olbers Paradox it became, and Olbers Paradox it remains. But the paradox still had no answer. Astronomers of the early 19th century moved past it without resolution, noting it as an interesting puzzle while directing their attention toward more tractable problems. Measuring stellar distances, mapping the structure of the Milky Way, cataloging nebulae, tracking the motions of double stars, the night sky remained dark. No one could explain why. The question drifted once more, and then in 1848, an answer arrived. From the last place anyone would have thought to look. Edgar Allan Poe was 40 years old and dying. He had spent his adult life producing literature of such sustained darkness and psychological precision that his name would become permanently associated with horror, grief, and the particular terror of minds unraveling under pressure. He had buried his young wife Virginia 2 years earlier after watching her die slowly from tuberculosis. He was drinking heavily. His finances were catastrophic. His health was deteriorating in ways he probably understood better than he admitted. He had perhaps a year left to live, though he did not know that yet. In this condition, he wrote a long prose poem he called Eureka. He described it as an essay on the material and spiritual universe. He delivered it as a lecture in New York to an audience of around 60 people. He considered it the crowning achievement of his life. He told his publisher it was the most important book ever written by a human being, which the publisher found difficult to evaluate commercially, and which most reviewers dismissed as the eccentric philosophical rambling of a talented writer operating outside his area of competence. They were wrong to dismiss it, not about everything. Eureka contains passages of genuine strangeness and some reasoning that does not hold up, but buried inside it expressed in prose rather than mathematics. Poe articulated something that the astronomers had missed entirely. He wrote that the darkness of the night sky proves the universe is not infinite and eternal, not because the universe is small, but because it is young, because light from the most distant stars and galaxies has not yet had sufficient time to reach us, because the universe began at some point in the past, and in the time since that beginning light, can only have traveled a finite distance. Beyond that distance, darkness. Not the darkness of empty space stretching forever, but the darkness of time itself. The darkness of light that has not arrived yet. The background of the sky, Poe wrote, must of course be zero because there is no part of that background which has not been or will not eventually be occupied by a star. But the stars which currently exist have not been shining long enough for their light to have crossed the distances involved. He had it, not perfectly, not in the form a physicist would require, not with the mathematical rigor that would eventually confirm it, but the essential insight was there expressed by a poet who was simultaneously grieving unwell, nearly broke, and apparently incapable of stopping himself from thinking about the structure of the cosmos. The universe is young. That is why the sky is dark. Nobody took Eureka seriously as cosmology. It was treated as literature at best. He was found delirious on a street in Baltimore, wearing clothes that were not his own, and died 4 days later without regaining full coherence. He was 40 years old. The answer he had glimpsed died with him at least for a while. It would take another century before physicists and astronomers assembled the pieces fully enough to confirm what Poe had understood intuitively. The universe did have a beginning. Time did start. Light from the farthest reaches of what is now observable. Space took billions of years to arrive, and light from beyond the observable horizon has not arrived at all and never will. The darkness is not the darkness of infinite empty space. It is the darkness of finite time. The night sky is dark because the universe is not old enough to be bright. But to understand why that answer is so devastating and so beautiful, we need to do something Halley and Chéseaux and Olbers could not do. We need to demolish one by one all the apparently reasonable solutions that turn out to be insufficient, because the real answer only reveals its full depth once you understand exactly why everything else fails. The next chapter examines the solutions that almost work and why the universe refuses to let them. Before we reach the real answer, we need to clear the ground, because the human mind, when confronted with a paradox, does not sit patiently with the discomfort. It reaches for solutions. It constructs explanations. It finds nearby ideas that seem like they might fit and tries them against the problem the way you might try a series of keys against a lock that will not open. Some keys look exactly right. Some slide in part way. Some almost turn before catching on something inside and refusing to go further. The history of Olbers' paradox is largely a history of keys that almost worked. Understanding why they fail is not a detour. It is the path. Because each failed solution teaches you something about what the darkness actually requires from the universe. Each one narrows the space of possible answers until only one remains standing, and that one answer, when you finally arrive at it, lands differently than it would if you had simply been told it at the beginning. The darkness earns its meaning through the failures that precede it. So, let us try the keys. The first solution most people reach for is distance itself. Stars are far away. Distant objects appear fainter. The farther you are from a candle, the less light reaches your eyes. This is not opinion or approximation. It is a precise mathematical relationship called the inverse square law. Double the distance between yourself and a light source and the brightness you perceive drops by a factor of 4. Triple the distance, brightness drops by a factor of 9. The relationship is exact because light spreads outward in 3 dimensions, covering an ever-increasing sphere of space as it travels, so any fixed area within that sphere intercepts a smaller and smaller fraction of the total light as the sphere grows. Apply this to stars, and the logic feels airtight. Nearby stars are bright, distant stars are faint. Unimaginably distant stars are unimaginably faint. Surely at sufficient distance, stars contribute effectively nothing to the brightness of the sky. Surely darkness wins simply because the universe is so extraordinarily large that almost all the stars in it are too far away to matter. This feels right. It feels intuitively correct, in the same way that many things feel intuitively correct before the mathematics gets involved. The mathematics is not kind here. The inverse square law does reduce the brightness of any individual star, with distance exactly as described. But an infinite universe does not contain individual stars. It contains shells of space. Imagine standing at the center of an enormous hollow sphere. The sphere has a certain radius, and its surface is covered with stars. Now imagine a second sphere, twice as large, also covered with stars. The stars on the second sphere are twice as far away, so each one appears 4 times fainter. But the surface area of the second sphere is 4 times larger than the first, which means it contains 4 times as many stars. 4 times fainter, 4 times more numerous. The total light contribution from both spheres is identical. Now imagine a third sphere 10 times larger. Stars 10 times farther away, 100 times fainter each. But the surface area is 100 times larger, containing 100 times more stars. Again, the total light contribution is identical to the first sphere. The cancellation is exact, perfect, mathematical. Every shell of the universe, regardless of how far away, contributes the same total brightness to your sky. And in an infinite universe, there are infinitely many shells. The sum is not merely large, it is infinite. Distance does not save you from the paradox. Distance is precisely cancelled by the increasing number of stars at greater distances, and the cancellation holds without exception throughout all of infinite space. The key slides in, it does not turn. The second solution feels more sophisticated. Perhaps something absorbs the light before it reaches us. The universe between stars is not perfectly empty. Clouds of gas and dust drift through interstellar and intergalactic space. Perhaps these clouds intercept starlight from distant sources, absorbing it before it can accumulate into the overwhelming brightness the paradox predicts. Perhaps the universe contains its own natural shielding, a cosmic filter that softens the otherwise intolerable glare of infinite stars. Chéseaux proposed this in 1744. It is a sensible idea. It is also thermodynamically impossible as a solution to Olbers' paradox, and the reason why is one of the most elegant demonstrations of physical law in the history of the problem. Consider what happens to matter when it absorbs radiation. It heats up. This is not a special property of dust clouds in space. It is a universal property of matter everywhere. When photons strike a material and are absorbed rather than transmitted or reflected, their energy transfers to the absorbing material, increasing its temperature. Your skin warms in sunlight for exactly this reason. Dark clothing heats up faster than light clothing in summer for exactly this reason. Matter that absorbs light becomes hot. Now apply this to a hypothetical light-absorbing medium filling intergalactic space in an infinite eternal universe. In this universe, stars have been shining forever. The absorbing medium has been absorbing their light forever. The energy of infinite starlight accumulated over infinite time has been pouring into this medium without interruption. What is the temperature of a substance that has been absorbing infinite energy for infinite time? It is the temperature of a star's surface. The absorbing medium, given infinite time to absorb infinite radiation, must reach thermal equilibrium with the stars themselves, and then radiate that energy back outward. A glowing medium, filling all of space, produces exactly the same sky as a sky full of directly visible stars. You have not eliminated the brightness. You have merely added an intermediary step before it arrives at your eyes. The cosmic fog saves nothing. An absorbing medium in an infinite eternal universe does not darken the sky. It becomes the sky, blazing uniformly in every direction. The key enters, it catches, it does not turn. The third solution is more modern, and it is the one that most people reach for today when they have some familiarity with cosmology. The universe is expanding, galaxies are moving away from us. The light from receding sources is stretched by that recession into longer wavelengths, shifting toward the red end of the spectrum, losing energy in the process. Surely this redshift removes energy from the light of distant galaxies, dimming them below what a static, infinite universe would predict. Surely an expanding universe solves the paradox. This solution is closer. It contains genuine physics and genuine insight, and it is still insufficient on its own, which is worth understanding carefully. Redshift does reduce the energy of photons from distant, receding galaxies. A photon that begins its journey as visible light may arrive at Earth as infrared radiation, carrying less energy than when it departed. In a universe expanding at the rate ours does, This represents a real and significant reduction in brightness. The expansion of the universe genuinely does dim distant sources beyond what a static universe would show. But here is the problem. Redshift alone in a universe that has existed forever and extends infinitely still does not produce a dark sky. The reason is subtle but important. Redshift reduces the energy of each individual photon. It does not eliminate the photons. And in a universe that has existed infinitely long, even redshifted photons from infinitely distant sources have had infinite time to arrive. The total number of photons reaching any point in an eternal infinite universe is still infinite, even after accounting for expansion and redshift. The energy per photon decreases, but the number of photons compensates. The sky may shift from optical brightness to infrared brightness, but it remains overwhelmingly catastrophically bright. You have changed the color of the furnace. You have not cooled it. There is a version of the expanding universe argument that does work, but it requires something additional. It requires the universe to have a finite age. It requires expansion to have started at a specific moment in the past, rather than having continued forever. The expansion rate matters, yes, but what matters more is the beginning. What matters more is that there was a first moment, and that is a different argument entirely. The key turns slightly, then it stops. There is something else inside the lock. Let us try one more failed solution because this one is instructive in a different way. Perhaps the universe is simply not infinite. Perhaps it has an edge. Kepler believed this. Many people find it intuitively appealing. If the universe is finite, if there are only a limited number of stars, then the total light they produce is finite, and perhaps that finite total spread across an infinite sky produces the darkness we observe. The problem here is twofold. First, the observational evidence does not support a simple finite static universe with an edge beyond which nothing exists. Modern cosmology, assembled through a century of increasingly precise observations, describes a universe that is either infinite in extent or so extraordinarily large that its curvature is immeasurably close to flat on any observable scale. The edge of the universe solution requires abandoning virtually everything else we know about cosmology. But second, and more philosophically interesting, a finite, static, eternal universe simply pushes the problem back without solving it. If the universe has always existed and contains a finite number of stars that have been shining forever, then in all that infinite time, the light from those stars has had infinite time to fill all of space to a uniform brightness. The stars may be finite in number, but they are infinite in duration. The energy they have poured into the universe over infinite time is still infinite. A finite eternal universe gives you the same blazing sky as an infinite one, just through a different mathematical path. The finitude of space does not save you. The eternity of time overrides it. The key does not fit at all. Now step back and look at what these failures have taught you. Dust does not work because matter in thermal equilibrium radiates back everything it absorbs. Distance does not work because the inverse square law is precisely cancelled by the increasing number of stars at greater distances. Redshift does not work alone because infinite time still delivers infinite photons. Finite space does not work because infinite time fills even finite space with infinite accumulated light. Every proposed solution that works within the framework of an infinite eternal universe fails. The failures are not incidental. They are systematic. They are telling you something. The universe is refusing every solution that preserves either its infinite extent or its infinite age. Every escape route closes. Every workaround collapses under examination. The darkness is pointing at something specific, and it will not let you look away from it. The only solution that survives all these objections simultaneously is the one Poe glimpsed from his grief and his illness and his extraordinary intuition in 1848. The universe is not eternal. It has a finite age. The darkness exists because light from the most distant sources has not yet had time to arrive. Not because space absorbed it, not because distance dimmed it into negligibility, not because expansion stole its energy, but because the journey has not been completed, because the universe began at a specific moment in the past, and in the finite time since that moment, light can only travel a finite distance. Beyond that distance is not empty space. It is not the edge of the universe. It is not darkness in any ordinary sense. It is the past itself, stretching back toward a beginning that light has not yet had time to cross. The sky is dark because time is young. This realization transforms the darkness above you into something completely different from what it appeared to be. When you look at the night sky and see darkness between the stars, you are not seeing the absence of anything. You are seeing the presence of a boundary. The boundary of how far light can have traveled since the universe began. Every dark patch of sky is a region from which light has not yet arrived. Not light that was absorbed or dimmed or deflected, light that is still en route. Light that began traveling billions of years ago and has not reached us yet. The stars are there, the galaxies are there. In all that darkness in every direction, ancient sources of light are burning or have burned and sent their photons outward into expanding space. But the universe is only 13.8 billion years old. Light travels at a fixed speed. The product of those two facts is a horizon, a sphere of observable space beyond which information has not reached us. Beyond that horizon, reality continues. But its light has not arrived. You are surrounded by light in transit. The darkness of the night sky is not empty space. It is a delay. It is the universe being younger than the distance to its contents. It is the shadow cast by a beginning. And that beginning, that specific finite moment when everything started, is what makes your existence in darkness possible at night. Without it, the sky would destroy everything standing beneath it. The forests would burn. The oceans would boil. The surface of Earth would reach the temperature of a stellar surface and remain there. Instead, you are comfortable. You are lying in the dark. The sky is quiet. The stars are small and distant and beautiful rather than an intolerable surrounding wall of fire. You are alive because the universe is young. That is what the darkness means. What comes next will take us deeper into that young universe, into what finite time actually implies for the structure of what we can see and what we cannot, and into the strange cosmic horizon that surrounds every observer everywhere in space, the boundary beyond which reality becomes permanently invisible. The darkness has a shape. Now we are going to find its edges. The universe began. That statement sits at the center of modern cosmology with a weight that is easy to underestimate because it has become so familiar. People hear it in documentaries, read it in textbooks, encounter it often enough that it starts to feel like background information rather than the most extraordinary claim human beings have ever made about reality. The universe began. Of course it did. Everyone knows that. But stop for a moment and feel what it actually means. Before the beginning, there was no space. Not empty space, not dark space, not space waiting to be filled. No space at all. There was no time. Not slow time, not suspended time, not time holding its breath before something happened. No time. There was no matter, no energy, no physics, no mathematics describing anything, no location in which anything could exist, no duration across which anything could change. There was nothing in the most absolute and literal sense of that word that the human mind can approach without sliding away from the concept entirely. And then there was something. This is not a comfortable idea. The human brain evolved to understand causes and effects unfolding inside an already existing universe, where things come from other things and nothing appears from nowhere. The question of what came before the Big Bang is not a question cosmology currently answers, not because scientists are being evasive, but because the question may not be well formed. Before implies time. Time began with the universe. Asking what came before the beginning is a little like asking what lies north of the North Pole. The grammar of the question contains an assumption that the physics does not support. What we can say is this. Approximately 13.8 billion years ago, everything that exists emerged from an extraordinarily hot, extraordinarily dense state and has been expanding and cooling ever since. That is the Big Bang, not an explosion happening inside space. The beginning of space itself, the beginning of time itself, the first moment of everything. And that finite age, 13.8 billion years, is the answer to Olbers' paradox. That is why the sky is dark. To understand precisely how you need to think about light, as information traveling at a speed that nothing can exceed. Light moves through empty space at approximately 300,000 kilometers per second. This is not merely the speed at which light happens to travel. It is a fundamental constant of the universe, a limit woven into the structure of space-time itself. Nothing with mass can reach it. No signal, no influence, no causal connection of any kind can propagate faster than this. The speed of light is the speed of causality, the maximum rate at which any event can affect any other event anywhere in the universe. This speed, vast as it is by human standards, is finite, and finite speed combined with finite time produces a finite distance. Light traveling for 13.8 billion years covers approximately 13.8 billion light years. That distance defines a sphere around every observer in the universe. Inside that sphere, light emitted at the beginning of time has had enough time to reach you. Outside that sphere, it has not. Outside that sphere, sources of light exist almost certainly, but their photons are still traveling toward you through expanding space. They have not arrived. They may never arrive for reasons we will reach shortly. This sphere is called the observable universe. It is not the edge of the universe. It is the edge of what you can currently see. It is the boundary of accessible history, the horizon beyond which the past has not yet communicated with your present. And because everything outside that sphere is invisible, the sky is dark. The numbers involved require a moment to absorb properly, because 13.8 billion years does not behave intuitively. The human brain handles thousands of years with moderate confidence, millions of years with some difficulty, and billions of years by quietly pretending they are roughly the same as millions, while hoping no one notices. So try this instead. Compress the entire history of the universe into a single calendar year. Every second of that year represents roughly 437 years of real cosmic time. The Big Bang occurs at the first instant of January 1st. By late January, the first stars are igniting inside the darkness of the early universe. The Milky Way begins forming around March. Our Sun and Solar System do not appear until early September, more than 8 months into cosmic history. The first complex life on Earth emerges in late October. The dinosaurs appear around Christmas Day and vanish by December 30th. All of recorded human civilization, every empire and every language and every war and every scientific discovery and every work of art ever created occupies the final 12 seconds before midnight on December 31st. The James Webb Space Telescope launches in the last fraction of the last second. Within that same compressed year, the light from JADES-GS Z140 began traveling in the first week of January, before our galaxy existed, before our star existed, before Earth existed. That light traveled for 11.5 months of cosmic time before reaching a telescope built in the last instant of the last day. The observable universe is 13.5 billion years of light travel in every direction. The darkness beyond it is everything that has not yet had time to communicate with us. And in a universe this young by cosmic standards, that darkness is enormous. But there is another layer to this that makes the answer more astonishing still. The universe is not merely old enough that light from distant sources has traveled a long time to reach us. The universe is expanding. Space itself stretches while light travels through it. And this expansion means that the actual present-day distance to the edge of the observable universe is not 13.8 billion light-years. It is approximately 46 billion light-years in every direction. This confuses people initially because it sounds impossible. If the universe is only 13.8 billion years old and nothing travels faster than light, how can anything be 46 billion light-years away? The answer is that galaxies at the edge of the observable universe were not 46 billion light-years away when they emitted the light we are now receiving. They were much closer. But in the time since that light began traveling toward us, the universe has continued expanding, carrying those galaxies farther away from us, even as their ancient photons crossed the intervening space. Space expanded around the photons while the photons traveled through it. The photons moved at the speed of light relative to their immediate local space, but that local space was itself being stretched, elongating the journey. so that by the time they arrived, the source was far more distant than it had been at departure. Imagine walking forward on a moving walkway that is itself being stretched while you walk. You move at a fixed speed relative to the walkway beneath your feet, but the walkway is continuously lengthening, carrying your destination farther away, even as you approach it. The time you take to arrive depends on both your walking speed and the rate of stretching. Photons crossing an expanding universe face exactly this situation. The observable universe is therefore a sphere roughly 93 billion light-years in diameter. Within that sphere lies everything humanity has ever observed or will ever observe, with instruments that detect electromagnetic radiation. Everything outside it, whatever it contains, however much of it exists, however many galaxies and stars and worlds and possible civilizations, all of it is beyond our reach. Not temporarily beyond our reach, waiting for better telescopes. Permanently beyond our reach. Their light, even light emitted at the moment of the Big Bang, will never reach us, because the expansion of the universe carries them away faster than their photons can travel toward us. The darkness surrounding the observable universe is permanent. It is a horizon we can never cross and never see past, and yet that horizon exists only because time is finite. Without a beginning, without a moment when everything started, there would be no horizon. There would only be fire. In 1964, two radio astronomers at Bell Laboratories in New Jersey, named Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna originally built for satellite communications. The antenna was extraordinarily sensitive, designed to detect faint microwave signals, and Penzias and Wilson were trying to calibrate it carefully for use in radio astronomy. They kept encountering a problem. Wherever they pointed the antenna in every direction across the sky, they detected a faint, persistent hiss of microwave radiation that should not have been there. It was not coming from the galaxy. It was not coming from the sun. It was not coming from any identifiable source. It came equally from every direction, a uniform background noise filling the entire sky with the same gentle whisper, regardless of where the antenna pointed or what time of day or year they made the measurement. They checked their equipment methodically. They verified their calibration. They looked for technical explanations. At one point, they discovered that pigeons had been roosting inside the horn of the antenna and leaving what Penzias and Wilson diplomatically described in their eventual scientific paper as a white dielectric material on the interior surfaces. They cleaned the antenna thoroughly. They removed the pigeons with considerable effort and presumably some personal inconvenience. The hiss remained. It was not pigeons. It was the oldest light in the universe. What Penzias and Wilson had accidentally discovered was the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, the ancient heat of the early universe, stretched by 13.8 billion years of cosmic expansion from the blazing plasma of the infant cosmos into microwave radiation so cool and so uniform that it fills all of observable space with a temperature of approximately 2.7 degrees Kelvin, just barely above absolute zero. This radiation is not coming from any particular object. It is not starlight. It is not galactic emission. It is the echo of the moment roughly 380000 years after the Big Bang, when the universe cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was an opaque plasma through which photons could not travel freely. After that moment, the cosmic fog cleared. Radiation streamed outward across all of space in every direction. Those photons have been traveling ever since. They are still traveling. They pass through you right now, through the walls of your room, through the atmosphere above you, through everything at a rate of roughly 400 photons per cubic centimeter per second. Ancient light arriving continuously from every direction in space, carrying information from an era when the universe was less than 400,000 years old. The night sky is not dark in the microwave spectrum. In microwaves, the sky glows with perfect uniformity in every direction. The darkness we see with human eyes is the darkness of our particular window onto reality. Change the window, and the darkness becomes light. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for their discovery. Their paper, published in 1965, was a model of scientific understatement. They described detecting a noise temperature duty of approximately 3.5 degrees Kelvin for which no explanation was found. In an accompanying paper in the same journal, Princeton cosmologists Robert Dick Jim Peebles, Peter Roll, and David Wilkinson explained that this noise was exactly the cosmic microwave background that Big Bang cosmology predicted should exist. The two groups had arrived at the same conclusion from opposite directions simultaneously, one by building a detector exquisitely sensitive enough to find ancient light accidentally, the other by calculating that ancient light should be findable. It remains one of the most remarkable confluences in the history of science. The echo of the beginning had been predicted theoretically and discovered accidentally by two researchers who initially suspected plumbing problems and birds. The cosmic microwave background is direct evidence that the universe had a hot, dense beginning. It is the fingerprint of the moment the cosmos became transparent. And because it exists, because this ancient radiation fills space uniformly and precisely as Big Bang cosmology predicts, we know the universe is young. We know it began. We know why the sky is dark. The darkness is not absence, it is age. Now, return to Olbers' paradox, with everything assembled. An infinite, eternal universe produces a blazing sky. Dust cannot cool it, distance cannot dim it, redshift alone cannot darken it, only a finite age can. Only the existence of a beginning, a specific moment before which there was no light. You can explain why you are lying in darkness right now, rather than being incinerated beneath a sky as bright as the surface of the sun at every point. The 13.8 billion year age of the universe means that light from sources beyond approximately 46 billion light-years away has not reached us. Most of the universe, if it extends much beyond the observable sphere, is hidden behind a horizon of finite time. The stars within the observable universe produce light. Yes, their combined contribution fills the sky with photons. But that contribution spread across the enormous dark sky produces only the faint scattered points we see as stars and galaxies, tiny bright objects against overwhelming blackness rather than a uniform wall of fire. The darkness wins because time is finite. And time is finite because there was a beginning. The night sky is dark because the universe was born. That sentence is not poetry, it is physics. The darkness above you tonight is a direct observable physical consequence of the Big Bang. You do not need a telescope to see evidence of the beginning. You only need to look up on a clear night and notice what most of humanity has noticed since before history began. The sky between the stars is black. That blackness is the Big Bang's most visible signature. It hangs above every human being who has ever lived, announcing the finite age of the universe to anyone who thinks carefully enough to ask why darkness should be there at all. Edgar Allan Poe, grieving and ill and nearly out of time himself, looked at that darkness in 1848 and understood something about it that the professional astronomers around him had missed. The darkness told him the universe was young, that light had not had time to arrive, that somewhere behind the observable horizon reality continued beyond what any human eye could reach. He was right. He was right in the final year of his life writing prose poetry about the mind of God, and he was right in ways that would take another century of physics and radio astronomy and accidental pigeon-related discoveries to confirm. The sky is dark. The universe is young. There was a beginning. Now we need to go further, because the horizon that makes the darkness possible is not merely a boundary of what we can see, it is a boundary of what can ever reach us. And beyond that boundary, the universe continues into permanent invisibility, containing whatever it contains across distances that expansion renders forever inaccessible. The darkness is not just the past. It is also the unreachable present and the forever hidden future of everything beyond our cosmic shore. The next chapter examines what lies in that permanent darkness and what it means to be surrounded by a universe you can never fully see. There is a region of the universe from which light is traveling toward you right now. It has been traveling for billions of years. It left its source long before Earth existed, long before the sun ignited, long before the Milky Way finished assembling itself into the spiral galaxy we inhabit. That light has crossed an almost incomprehensible distance through expanding space, dodging nothing, absorbed by nothing, deflected by nothing, simply moving at the only speed the universe permits for massless particles, crossing void after void after void for billions of years in a straight line aimed through pure geometry at a small blue planet orbiting an ordinary star. It will not arrive, not because something will stop it, not because the universe will end before it gets here, not because any obstacle lies in its path. It will not arrive because the space between that source and Earth is expanding faster than the light can cross it. The gap is growing. The photons are moving at the maximum speed the universe allows, and the universe is defeating them anyway, not through force, but through geometry. Space itself is widening between the photons and their destination faster than they can close the distance. Those photons will travel forever. They will never reach anything. This is one of the loneliest facts in cosmology, and it is not a special case. It describes the fate of light from an enormous fraction of everything that exists. To understand how this is possible without violating the rule that nothing travels faster than light, you need to hold two ideas simultaneously. First, the speed of light is a local limit. Nothing in the immediate vicinity of any observer can move through space faster than light. This remains absolute. It is not violated. Second, space itself is not subject to this limit. Space can expand at any rate. The distance between 2 points can increase faster than light could travel between them, not because anything is moving through space faster than light, but because space itself is generating new distance between those points continuously. Imagine two ants on an enormous rubber band standing some distance apart. Each ant can walk at a fixed maximum speed. Now, stretch the rubber band. The ants are not moving relative to their immediate surroundings. They are simply standing in place. But the distance between them is increasing because the rubber beneath their feet is expanding. If the rubber stretches fast enough, the ants can walk toward each other at full speed and still move apart. Neither ant has violated any rule about walking speed. Space itself has simply generated more distance between them than their walking can overcome. Photons crossing the universe face exactly this situation. They move through space at the speed of light relative to their local surroundings. But the space through which they move is itself expanding, continuously generating additional distance between the photon and its destination. In regions of the universe sufficiently far away, the expansion rate is high enough that this generated distance exceeds the photon's travel speed. The light makes progress in its local space, but loses ground against the expanding geometry of the universe as a whole. There is a distance beyond which this condition holds permanently. Astronomers call it the Hubble radius, the boundary beyond which the expansion rate of space exceeds the speed of light. Sources beyond this boundary are receding from us faster than light, not through their own motion through space, but through the expansion of space between us. Light they emit today will never reach us. It will travel outward through expanding space for the rest of the universe's lifetime and never close the gap. That boundary currently lies roughly 14 billion light-years away in every direction. Beyond it, reality continues. Galaxies exist there. Stars burn. Perhaps worlds orbit them. Whatever is there is real, as physically real as the galaxy you inhabit right now, but it is permanently invisible. Not invisible because of dust or distance or interference. Invisible because the universe is expanding between us and those sources, faster than information can cross. The observable universe, the sphere roughly 46 billion light-years in radius within which ancient light has already reached us, is not the same as the sphere of sources currently able to communicate with us. These two boundaries differ in an important and somewhat vertiginous way. The observable universe contains everything whose ancient light has already arrived. Some of those sources are now so far away, carried by billions of years of expansion, that they are already beyond the Hubble radius. Their ancient light reached us, emitted when they were much closer, but new light they emit today will never reach us. We can see their past, we cannot see their present, we cannot see their future. The boundary of what can ever reach us in the future is called the cosmic event horizon. It lies somewhat beyond the current Hubble radius, accounting for the fact that the universe's expansion rate changes over time. Everything beyond the cosmic event, cosnot, cosine, dark is not merely presently invisible, it is permanently, irrevocably, forever invisible. No future telescope, no matter how sensitive, no matter how many years it operates, will ever detect a photon from beyond that boundary. Those sources have passed over an edge from which no light returns. The universe is therefore divided from the perspective of any observer anywhere into three regions. The first is the observable universe, everything whose ancient light has already arrived or is currently arriving. This contains hundreds of billions of galaxies, the entire accumulated record of cosmic history, accessible to electromagnetic observation. The second is the region beyond the observable universe, but within the cosmic event horizon. Sources there have not yet sent light that has reached us, but light they emit now could in principle eventually arrive. This region remains theoretically accessible to future observation, though in practice, as the universe continues expanding, it will contribute less and less new observable content over time. The third region is beyond the event horizon, permanently, absolutely, forever beyond reach. Whatever exists there cannot communicate with us through any means limited by the speed of light. It might as well exist in a different universe, and in a meaningful physical sense it does. It is causally disconnected from us. Its history will never intersect ours again. That third region almost certainly contains more matter, more stars, more galaxies, more of everything than the observable universe we inhabit. Possibly vastly more, possibly infinitely more. If the universe extends infinitely beyond our horizon, we will never know what is there. Not because we lack the technology, because the physics itself prevents the information from reaching us. Now consider what this means from the perspective of time. The cosmic event horizon is not static. It changes as the universe evolves. In the current era, the universe's expansion is accelerating, driven by what cosmologists call dark energy, a mysterious component of the universe associated with the energy of empty space itself that pushes the expansion rate higher over time rather than allowing gravity to slow it. As expansion accelerates, the event horizon contracts. Sources that are currently technically capable of communicating with us will progressively cross the horizon and become permanently invisible. The observable universe is shrinking in terms of what can ever reach us, not because the universe is getting smaller, but because the expansion is getting faster. In the far future, if dark energy continues driving acceleration, galaxies that are currently visible will eventually redshift beyond detectability. Their photons will be stretched to such long wavelengths, carrying such vanishingly small energies that no instrument could detect them. One by one, distant galaxy clusters will fade from view. The cosmic landscape available to any observer anywhere will become progressively emptier as more and more of the universe recedes beyond the horizon. In the extremely remote future, trillions of years from now, the observable universe for any remaining civilization may consist of little more than their own local galaxy or galaxy cluster gravitationally bound together, and therefore not being carried away by expansion. Everything beyond that local island will have vanished into permanent invisible darkness. The universe will appear to any observer who might exist then to be nearly empty, nearly dark, a single galaxy floating alone in infinite black space. They will not know about the hundreds of billions of galaxies that once existed within the observable universe, because those galaxies will have vanished beyond the horizon before those observers evolved. They will not have access to the cosmic microwave background, redshifted by then to wavelengths so long as to be effectively undetectable. They will have no observational evidence that any other galaxies ever existed. If they are scientists, they may look at the apparently empty universe and struggle to explain how their single isolated galaxy came to exist. They will be surrounded by a universe vastly larger and richer than anything they can see, and they will have no way to know it. The darkness that surrounds them will not be the darkness of an empty universe. It will be the darkness of an invisible one. There is a strange emotional weight to this that takes time to fully settle. We exist as a civilization at a fortunate moment in cosmic history. The universe is old enough for stars and galaxies and planets and life to have formed, but it is young enough that the cosmic microwave background is still detectable, that distant galaxies are still visible across billions of light years, that the evidence for the Big Bang is still accessible to observation. The full archive of cosmic history, at least the electromagnetic portion of it, is still available to read. Future civilizations, if they exist in the remote future, will have lost most of this archive. The universe will have expanded it beyond reach. They will inherit a cosmos that looks impoverished compared to ours, not because it is impoverished, but because most of it will have slipped beyond the horizon of knowability. In this sense, we are living during one of the best possible eras for cosmology. The universe is revealing itself now in ways it will not always be able to. The evidence of its origins is still fresh enough to detect. The cosmic microwave background still fills the sky with ancient light. Distant galaxies still send their photons across accessible distances. The observable universe is currently at something close to its maximum information content, at least from the perspective of what we can detect. This will not last. The window is open now. It will not always be. And yet, even surrounded by all this permanent darkness, even knowing that most of the universe is and will remain forever invisible, there is something quietly extraordinary about the fraction we can see. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. The total number of stars in the observable universe is estimated at approximately 1 followed by 24 zeros, a number so large that if you counted 1 star per second without stopping, you would need roughly 3 million times the current age of the universe to finish. All of that exists within the thin, bright shell of the observable universe, the region where finite time has allowed ancient light to arrive. It represents perhaps a tiny fraction of everything that exists beyond our horizon. The universe we can see may be an almost negligible sample of the universe, that is. And every observation we make, every galaxy we photograph, every spectrum we analyze, every ancient photon we catch with gold-coated mirrors drifting through space near L2 comes from within that thin, accessible shell. The James Webb Space Telescope, observing galaxies like JADES-GS from near the edge of the observable universe, is reaching toward the boundary of what finite time allows. It is catching photons that have been traveling since before Earth existed, photons that originated near the cosmic dawn within the earliest accessible pages of observable history. Beyond the most distant galaxy Webb can detect, the observable universe continues for a short distance farther back toward the cosmic microwave background itself, the wall of ancient plasma, beyond which electromagnetic observation cannot reach. That wall, at a redshift of approximately 1100, represents the absolute optical horizon of the universe. Behind it, the universe existed, but was opaque. Its light cannot cross the barrier because it was scattered continuously through hot plasma before recombination allowed photons to travel freely. The darkness at the edge of the observable universe is therefore twofold: the darkness of time photons that have not yet arrived from sources beyond our horizon, and the darkness of opacity photons that cannot reach us at all because they were scattered before the universe became transparent. We are surrounded, completely surrounded by regions of the universe that are invisible to us for one reason or another. The darkness of the night sky is not merely the absence of light. It is the presence of multiple overlapping boundaries, the horizon of finite time, the wall of ancient plasma, the receding edge of everything expansion is carrying beyond reach. The sky is dark because we are enclosed within a finite bubble of accessible history, surrounded by an invisible universe that extends in every direction beyond anything we can ever detect. There is a particular kind of vertigo that comes from understanding this fully. You are not standing at the center of the universe in any privileged physical sense. Every point in the universe has its own observable sphere, its own horizon, its own bubble of accessible history. An observer in a galaxy 2 billion light-years away has a completely different observable universe from yours, overlapping but not identical, containing regions of space you cannot see and lacking regions of space you can. Every observer, everywhere in the cosmos, is enclosed within their own unique bubble of knowable reality, surrounded by the same permanent darkness, looking outward at the same fundamental limit imposed by finite time and expanding space. The darkness is universal, not in the sense that it is the same darkness everywhere, but in the sense that every observer everywhere faces it. Every conscious being, wherever it might exist in this universe, looks outward and eventually reaches the edge of what finite time has made visible, and beyond that edge, the same permanent darkness waits. You are not alone in the darkness. You are simply located inside a finite sphere of light, within an infinite darkness that every observer shares, each from their own unique vantage point, each surrounded by their own unique slice of the inaccessible universe. That darkness is not emptiness. It is fullness that cannot reach you. Somewhere out there, beyond the cosmic horizon, beyond the expanding boundary, that expansion makes permanent beyond the wall of ancient plasma that marks the edge of electromagnetic observation, reality continues into distances and extents that no measurement we can ever make will fully constrain. It may be infinite, it may contain structures we cannot imagine, it may be in its totality so much larger than the observable universe that the 2 trillion galaxies we can see represent a fraction so small it approaches zero. The darkness that answers Olbers Paradox is not the simple darkness of empty space. It is the darkness of a universe so enormous, so old, and so fast in its expansion that most of it is permanently hidden from every observer within it. And yet here in this thin, bright shell of accessible history, something extraordinary happened. Matter organized itself into stars. Stars forged heavier elements. Planets formed. Chemistry became biology. Biology became consciousness. Consciousness became curious. And curiosity built instruments that can catch ancient photons from galaxies near the dawn of time, reading the universe's history from within a bubble of light surrounded by permanent darkness. We are not the center of the universe, but we are, as far as we know, the only part of it that has learned to read the darkness. What the darkness has to tell us goes deeper still, because the darkness is not entirely dark. Right now above you, ancient light fills the sky in wavelengths your eyes cannot detect. The faint echo of the beginning itself surrounds you in every direction, invisible and constant, and older than everything else you will ever encounter. The universe's first light is here. It has always been here. It arrived long before you did, and it will remain long after. The next chapter turns toward that ancient light and toward what it reveals about the earliest accessible moment in cosmic history, the boundary beyond which even the James Webb Space Telescope cannot see, and what humanity has learned from catching the oldest photons the universe has ever released. Right now you are bathed in ancient light. Not the light from a lamp nearby or the faint glow of a screen somewhere in the room or the distant illumination of a city softening the horizon outside your window. Ancient light. Light that has been traveling through the universe for approximately 13.8 billion years. Light that originated in conditions so extreme that matter itself could not hold together, that was scattered and scattered and scattered through a blazing plasma for hundreds of thousands of years, before finally being released to travel freely across the cosmos. Light that predates every star, every galaxy, every planet, every ocean, every living thing that has ever existed anywhere in the observable universe. It is passing through you right now, through the walls of your room, through the atmosphere above you, through the planet beneath you. It arrives from every direction simultaneously, a perfectly uniform whisper of ancient radiation filling all of space in every direction with the same gentle intensity, the same temperature, the same faint and extraordinary message from the earliest accessible moment in cosmic history. You cannot see it. Your eyes are not sensitive to the wavelengths it carries, but it is there, constant and patient and ancient beyond anything else your body will ever encounter, surrounding you, as completely as the air you breathe, as old as time itself allows anything visible to be. This is the cosmic microwave background, and it is the oldest light the universe can show us. To understand what the cosmic microwave background actually is, you need to return to the early universe one more time, not to the cosmic dark ages or the formation of the first stars, but to an even earlier moment, to an era when the universe was so hot and dense that atoms themselves could not exist. In the first hundreds of thousands of years after the Big Bang, the cosmos was filled with a plasma, a state of matter in which electrons have been stripped away from atomic nuclei by the intense heat and move freely through space. This plasma was opaque. Photons trying to travel through it were continuously scattered by free electrons, bouncing in random directions, unable to travel any significant distance before striking another charged particle and changing course. The universe during this era resembled an impenetrable fog, lit from within, brilliantly luminous in every direction but utterly opaque. Light existed in enormous quantities. It simply could not go anywhere. This continued for roughly 380,000 years. Then the universe cooled to approximately 3000 degrees Kelvin, a temperature at which electrons could finally settle into stable orbits around atomic nuclei, forming neutral hydrogen and helium atoms for the first time. The plasma cleared. Electrons were no longer free to scatter photons continuously. Light suddenly found itself in a transparent universe, with nothing to stop it. The photons that had been trapped within the plasma were released all at once across the entire universe simultaneously. They streamed outward in every direction from every point in space. The accumulated radiation of 380,000 years of primordial plasma finally liberated to travel freely. This moment is called recombination, the era when matter and radiation decoupled from one another and went their separate ways. Those photons have been traveling ever since. For 13.8 billion years they have crossed expanding space. The universe has stretched dramatically since they were released, and that stretching has stretched the photons, along with it shifting their wavelengths from the infrared and visible light of the hot early universe into the microwave wavelengths they carry today. The temperature they represent has dropped from 3000 degrees at release to approximately 2.725 degrees Kelvin, now just barely above absolute zero, the coldest natural temperature in the observable universe. Colder than any cloud of interstellar gas, colder than the surface of Pluto, colder than almost anything that exists. The cosmic microwave background is the universe's own body, heat cooled almost to nothing by billions of years of expansion, but still present, still measurable, still carrying within its faint variations the seeds of everything that would eventually form in the cosmos above it. When astronomers map the cosmic microwave background with precision instruments, they find something that initially sounds simple and then becomes extraordinary. The temperature is almost perfectly uniform across the entire sky. Whichever direction you point a microwave telescope, the background radiation arrives at almost exactly the same temperature. Not approximately the same temperature, not roughly the same to 1 part in 100,000. The entire observable sky, every direction, every region, every point across the full sphere of accessible space glows at the same temperature to extraordinary precision. This uniformity is so perfect that it requires an explanation, because regions of the sky on opposite sides of the observable universe are too far apart to have ever been in causal contact with each other. If the universe simply expanded smoothly from the Big Bang, light from one side has not had time to reach the other side. How can they know to be at the same temperature? The answer lies in a period called cosmic inflation, a hypothetical era of extraordinarily rapid exponential expansion in the first tiny fraction of a second after the Big Bang, during which the universe expanded from a volume smaller than a proton to something roughly the size of a grapefruit in an interval so brief that current physics struggles to describe it meaningfully. During inflation, regions that were originally in causal contact with each other, sharing the same conditions and the same temperature, were stretched apart to distances far beyond what the subsequent 13.8 billion years of more moderate expansion could separate. They retained their shared temperature because they had been in contact before inflation drove them apart. The uniformity of the cosmic microwave background is evidence of inflation. Evidence that the universe underwent something almost impossibly fast at its very beginning, something that seeded the vast scales of the observable universe from a region originally tiny enough to be quantum mechanical in nature. But the cosmic microwave background is not perfectly uniform, and those imperfections matter more than the uniformity. Scattered across the nearly uniform background are tiny fluctuations in temperature variations of roughly 1 part in 100,000 above or below the average. Fractional differences so small they would be invisible to any instrument less sensitive than the dedicated space observatories built specifically to detect them. The European Space Agency's Planck satellite, operating from 2009 to 2013, mapped these fluctuations across the entire sky with extraordinary precision, producing an image that looks at maximum contrast enhancement, like a faint pattern of slightly warmer and slightly cooler patches spread across a nearly featureless background. These tiny fluctuations are not noise, they are not measurement errors, they are the seeds of everything. Those slightly denser regions in the early universe, those areas where matter was fractionally more concentrated, became the sites where gravity had the most to work with. Over hundreds of millions of years, matter fell toward those denser regions, amplifying the initial fluctuations gradually into larger and larger structures. Eventually, the slight overdensities became the first dark matter halos. Gas fell into those halos and formed the first stars. Stars gathered into the first galaxies. Galaxies merged into clusters. Clusters organized into the vast cosmic web of filaments and voids that characterizes the large-scale structure of the universe today. Every galaxy that has ever existed, including the Milky Way, including JADES-GS 140, traces its origin to a specific tiny temperature fluctuation in the cosmic microwave background. The map of the CMB is a baby picture of the universe. It shows in its faint variations the precise initial conditions from which all cosmic structure grew. You can look at that map and point to a slightly warmer patch and say somewhere along the line of sight through that patch there is a galaxy cluster today that grew from that seed. The connection is direct. The fluctuation in the ancient plasma became the overdensity that gravity amplified, that became the dark matter halo, that became the galaxy, that became the cluster. The baby picture contains the adult inside it, if you know how to read the development. Now consider what this means for the darkness of the night sky. The cosmic microwave background is the oldest light the universe can show us through electromagnetic observation. It represents the wall of the observable universe. In the time direction, the earliest moment from which photons can have traveled freely to reach us. Earlier than recombination, the universe was opaque. No photons from before that era can reach us directly. The CMB is the horizon in time, just as the event horizon is the horizon in space. Between the CMB and the present lie 13.8 billion years of cosmic evolution. Stars formed, lived, and died. Galaxies assembled and merged. Heavy elements accumulated through stellar nucleosynthesis. Planets formed around later generations of stars. Life emerged on at least one of them. Civilization developed, telescopes were built, and the James Webb Space Telescope, operating in the infrared, is now probing the era just after the CMB, the cosmic dawn, the period when the first stars and galaxies emerged from the darkness that followed recombination. The era that Poe guessed about, and Olbers could not reach, and Hubble could only glimpse the edges of. JADES-GS 140, at a redshift of approximately 14, exists only about 290 million years after the Big Bang. That places it astonishingly close to the CMB, separated from the wall of ancient plasma by a relatively thin slice of cosmic history on the full 13.8 billion year timeline. Between the moment the universe became transparent and the moment this galaxy emitted the light, Webb detected less than 300 million years passed. 300 million years sounds immense by human standards. On the cosmic timeline, it is the blink of an eye. Webb is therefore not merely observing a distant galaxy, it is observing the universe in the first pages, after its oldest visible chapter. It is reading the text that follows immediately from the baby picture. It is watching what happened when the seeds in the CMB began to grow. And what Webb found there surprised the astronomers who built it. The early universe near the cosmic dawn was expected to be populated by small, primitive, relatively faint galaxies. The seeds in the CMB were tiny. Growing those seeds into large, luminous structures was expected to take time for matter to accumulate, for stars to form and enrich surrounding gas, with heavier elements for galaxies to merge and grow through hierarchical assembly. The cosmic dawn was supposed to be a quiet beginning, modest structures in a young universe still finding its footing. Instead, Webb found galaxies that were unexpectedly bright, unexpectedly massive, unexpectedly developed. The early universe was not quiet, it was blazing. Stars were forming with extraordinary efficiency. Galaxies were assembling faster than models predicted. The cosmic dawn was not a gentle sunrise. It was an explosion of structure, erupting from the seeds left by the Big Bang, with an urgency that current theoretical understanding struggles to fully explain. JADES-GS Z140 is one of the strongest examples. A galaxy bright enough to be detected across 13.5 billion light-years of expanding space, existing only 290 million years after the Big Bang, already forming stars at rates, suggesting substantial organized structure in the young universe. The galaxy is not supposed to be there in its current form, according to the assumptions built into many cosmological simulations. And yet there it is, its ancient photons arriving at Webb's mirrors, quietly insisting that the early universe was more productive than the models assumed. This does not break cosmology. The fundamental framework remains intact. The Big Bang happened. Inflation seeded the CMB fluctuations. Dark matter provided the gravitational scaffolding. All of that continues to explain the large-scale structure of the universe with extraordinary precision. What Webb is revealing is that the details of star formation, efficiency, and galaxy assembly in the very early universe may have worked differently than previously thought. The seeds grew faster than expected. The first gardeners of cosmic structure were more aggressive than the models allowed for. There is a connection here to Olbers' paradox that is worth dwelling on. The darkness of the night sky answers the paradox by pointing to a finite age. The universe is young, therefore light from the most distant sources has not arrived. Therefore the sky is dark rather than blazing. That answer requires a beginning, a specific moment, before which there was no light. The cosmic microwave background is the direct evidence of that beginning. It is the oldest light the universe can show us. The photons released at the moment the cosmos first became transparent, the visible boundary of finite time. And the first galaxies that Webb is now observing, galaxies like JADES-GS Z140, sit just on the other side of that boundary from us. They are the first structures that emerged after the universe became transparent. They are the first complex objects that the freed photons of the CMB illuminated as they streamed outward across a newly transparent cosmos. They represent the universe taking its first steps from the hot, simple state recorded in the CMB toward the complex, differentiated cosmos we inhabit today. The darkness of the night sky, the CMB, and the ancient galaxies Webb observes are therefore not separate phenomena. They are three aspects of the same story. The darkness exists because time is finite. Time being finite means there was a beginning. The CMB is the light from that beginning, the oldest accessible chapter of cosmic history. The first galaxies are what came next, the universe beginning to build its long future from the seeds that beginning planted. Every piece connects to every other. The simplest question, why is the sky dark, leads through history and mathematics and the deaths of stars and the birth of planets to the most profound discovery in the history of human inquiry. The universe began, and the evidence for that beginning is visible on every clear night in the darkness between the stars to anyone willing to ask why it should be there. Now think about what you are doing when you look at the night sky. You are looking at a record of finite time. The nearby stars appear to you as they existed years or decades ago, their ancient light still arriving across the relatively modest distances of our galactic neighborhood. The galaxies visible to the naked eye appear as they existed millions of years ago. The faint smudge of the Andromeda galaxy, barely visible on a clear moonless night away from city lights, shows you a galaxy as it existed approximately 2.5 million years ago. Before our species existed, before the genus Homo existed, before many of our nearest evolutionary relatives walked any surface that would eventually become familiar. And the most distant objects Webb can detect show you the universe as it existed when it was less than 300 million years old, when the first galaxies were just beginning to emerge from the darkness that followed the first. Light. The entire observable universe is a time capsule. The darkness between the objects in it is the boundary of that capsule, the edge of how far finite time has allowed light to travel since the beginning. Every photon reaching your eyes or Webb's mirrors or any detector ever built by any civilization anywhere is a message from the past delayed by the finite speed of light traveling through a universe of finite age. And the darkness that surrounds those photons, the black sky between every star and every galaxy, and every ancient smudge of light at the edge of observation, is not the absence of something, it is the presence of a boundary, the horizon of finite time, the shadow cast by the beginning of the universe itself. You are looking at the Big Bang every time you look at a dark night sky and notice the darkness. Not at the event itself, which occurred before electromagnetic observation was possible, but at its most visible consequence. The darkness is the Big Bang's clearest signature, more constant than any telescope's observation, more accessible than any instrument, available to every human being who has ever looked upward on a clear night since the first moment our species developed eyes capable of seeing stars. The darkness has always been telling us this. We simply needed to learn how to listen. Now we go to the end. We began with darkness. Not the darkness of a power outage or a cloudy night or a room with the curtains drawn. The darkness of the sky itself, the black space between the stars that every human being who has ever lived has seen, has felt something about, has perhaps pointed at as a child, and asked a question that the nearest adult answered incompletely before moving on to something more manageable. The darkness that has been there every clear night since Earth formed, since the sun ignited, since the first eyes capable of detecting light evolved on this planet and turned upward toward the sky. We asked the simplest question, why is it dark? And the answer turned out to contain the entire history of the universe. Let us gather what we have found. The darkness of the night sky is not the absence of stars. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains hundreds of billions of stars on average. The total number of stars in the observable universe exceeds any number that human language handles gracefully. There is no shortage of light sources. The universe is extravagantly, almost incomprehensibly full of them. The darkness is not caused by dust or gas absorbing the light of distant stars. Any absorbing medium in an infinite eternal universe would heat to stellar temperatures and glow just as brightly as the stars it absorbed. The darkness is not saved by distance, because the inverse square law that dims individual stars with distance is precisely cancelled by the increasing number of stars at greater distances, every shell of the universe contributing equally to total sky brightness, regardless of how far away it lies. The darkness is not produced by the expansion of the universe alone, because expansion in an eternally old universe still delivers infinite photons across infinite time, changing their wavelengths, but not eliminating their accumulation. The darkness exists for one reason, and one reason only. The universe is young. It began 13.8 billion years ago. In the finite time since that beginning, light can only have traveled a finite distance. Sources beyond approximately 46 billion light-years away, accounting for the expansion of space during the photon's journey, have sent light that has not yet arrived. The sky is dark in the spaces between stars and galaxies, because in those directions, looking back through time, we are looking toward distances from which light has not yet reached us. Not light that was absorbed or dimmed or lost. Light that is still traveling. Light that will arrive in the future, some of it. Or light that will never arrive at all, because expansion is carrying its source beyond the event horizon faster than the photons can close the gap. The darkness is a delay. The darkness is a horizon. The darkness is the shadow of a beginning. Heinrich Wilhelm Olbers asked the question in 1823 and could not answer it. Johannes Kepler had asked it 2 centuries earlier and reached the wrong conclusion. Edgar Allan Poe glimpsed the right answer in 1848 through grief and intuition, and the peculiar clarity that sometimes accompanies minds working near the edge of their endurance. Arno Penzias and Robert Wilson confirmed the answer, accidentally in 1964, while trying to identify interference that turned out to be the oldest light in the universe. The Planck satellite mapped that ancient light with extraordinary precision and found within its faint variations the seeds of every galaxy that has ever existed. And the James Webb Space Telescope, drifting quietly near L2, is now reading the first pages of the story those seeds began, detecting ancient galaxies from near the cosmic dawn, catching photons that began traveling before Earth existed, before the sun ignited, before the Milky Way looked anything like the galaxy we call home. All of it connects. The darkness and the ancient light and the first galaxies and the cosmic microwave background and the Big Bang and the finite age of everything. One continuous thread running from the simplest observation any human being can make on any clear night to the deepest truth cosmology has yet uncovered. The sky is dark because the universe began. Now consider what it means to be the kind of creature that can know this. You are, as far as any evidence currently suggests, assembled from matter that was forged inside stars. The carbon in your body was produced through nuclear fusion in stellar cores. The oxygen you are breathing was released into space by dying stars and incorporated into the gas cloud that eventually became the sun and its planets. The iron in your blood was created in supernova explosions and scattered across interstellar space before gravity gathered it into the solar nebula that became Earth. You are, in the most literal physical sense available to science, a child of the universe's own history, a temporary arrangement of ancient stellar material held together by chemistry, animated by biology, capable for a brief time of asking questions about the cosmos that produced you. And among all the questions that creature has ever asked, the one that turned out to carry the most cosmological weight was the one that required nothing more than a clear night and a willingness to notice what was obviously there. Not a telescope, not a laboratory, not centuries of accumulated mathematics, just darkness and the question of why. Why is it dark? Because the universe began, because time started, because there was a first moment before which there was nothing. Not empty space, not darkness, not silence, nothing at all, and from which everything that exists emerged and has been expanding and cooling and complexifying for 13.8 billion years. Because light travels at a finite speed through space that has been expanding since that first moment, and in the time available most of the light from most of the universe has not yet reached you. Because you are located inside a thin bright shell of accessible history, surrounded by a permanent darkness that is not emptiness but fullness that cannot reach you, an invisible universe extending in every direction beyond the horizon that finite time imposes on every observer everywhere. Because the universe is not infinite and eternal, it is finite and young, and the darkness is how you can tell. There is a particular kind of humility that cosmology produces different from other kinds of humility. It is not the humility of feeling small, though, that is part of it. It is the humility of realizing that the most familiar things contain the deepest truths, that the question requiring the most profound answer was also the question that required the least specialized equipment to ask, that the darkness every human being has always seen was always already telling us something about the nature of time and the origin of the universe, waiting for someone to take it seriously enough to ask why it was there. Kepler asked, Olbers asked, Poe understood. Penzias and Wilson heard the answer, with a radio telescope pointed at apparently empty sky. And now Webb reaches toward the earliest galaxies, reading the universe's first legible chapter, from a distance of 13.5 billion light-years, catching photons that have been traveling since before this planet existed. The darkness was always the message. We simply needed time to learn to read it. And the message, when fully read, is not a diminishment. It does not make you smaller. It does not render human existence insignificant against the scale of a universe 93 billion light-years across, containing 2 trillion galaxies, containing more stars than any number in ordinary human vocabulary can comfortably represent. It makes you stranger and more extraordinary than that picture might initially suggest. Because in all that vast expanding darkness, in all those trillions of galaxies across billions of light-years of observable space, across the entire 13.8 billion year history of a universe that built itself from quantum fluctuations in the first fraction of a second after the beginning, one arrangement of stellar material on one planet, orbiting one star in one galaxy, learned to ask why the sky was dark at night. One arrangement looked at the darkness and did not simply accept it, did not treat it as background, did not walk past it towards something apparently more important. One arrangement stopped, looked up, and asked the question that nobody had thought to ask seriously for most of human history, and kept asking it through centuries of failed solutions and incomplete answers until the right answer finally emerged from radio telescopes and space observatories and patient mathematical reasoning. And it turned out to be the most extraordinary answer the universe has offered any observer we know of. The sky is dark because time began, and you assembled from the ashes of ancient stars living briefly on a small world in an ordinary galaxy, surrounded by the permanent darkness of a universe, too young to have filled the sky with all its light, are the part of the universe that found that out. Somewhere above you tonight, ancient light is still traveling. Photons from galaxies that will never be discovered are crossing expanding space in the darkness beyond the observable horizon, carrying information from cosmic eras that no instrument will ever detect. Photons from JADES-GS 140 have already arrived, already been caught, already been read. The galaxy they came from has continued evolving for 13.5 billion years since they departed, and the newer light from that evolution is somewhere in the space between that galaxy and this world still traveling not yet here. The cosmic microwave background surrounds you in every direction, the faintest light the universe can show, barely warmer than absolute zero, older than every star, older than every planet, older than every living thing. It passes through you without interruption, ancient and patient and constant, the universe's own memory of its earliest transparent moment, still present after all this time, and the night sky above you is dark. Dark because the universe is young, dark because time began, dark because most of the light that exists has not yet arrived, and some of it never will. Dark because you are enclosed within a finite sphere of accessible history, surrounded by an infinite darkness that is not empty, but is simply permanently beyond reach. The darkness is not the absence of the universe. The darkness is the universe announcing that it had a beginning. Every night you have ever spent beneath a clear sky, that announcement was there. In every direction you could look, written in the spaces between the stars, in the black that frames every point of ancient light, in the simple, obvious, undeniable fact that you could see the sky at night without being incinerated. The universe began. The sky is dark. And for a brief, extraordinary moment in the long history of that darkness, something inside the light learned to notice the difference.